what I think is funny is that like Comcast
Ridiculous.
tries to offer like 100, and it like, makes you pay almost $200, but like OX isn't capable of supporting that much bandwidth.
No, definitely not the way they do it. Definitely not.
Yeah, see,
All right.
I started at like, I think $50 a month for cable and internet, and then it went up to like 80, and at one point it was like at 120, and I'm like, why am I paying like?
That's what happened when I lived in my last apartment. I was like, screw you guys. You either change it or you're canceling. And
Yeah.
they changed it.
They would change it, but they're always like, oh, well, you can't do the introductory 50, it's got to be 60. And then the next
All
time
right.
it's like, oh,
Well,
we can't do 60.
Let's go ahead and get started. Last time, the very last thing that I mentioned from Tuesday was time complexity. So that's what we'll start with today. It's definitely one of those things where most professors will say that's well beyond the scope of an introductory class. Okay, so most of the time they won't even touch on this until you get to like a high upper division class at a 4-year university. It's like a 3rd year class at a 4-year university. But the concept, on the other hand, is very, very important. Okay, so what we'll do is we'll go with a spreadsheet to see how my colleague and I were duking it out. Remember the last time the company was downsizing down to me and one of my colleagues, and and my boss, not knowing anything about time complexity, does not want to use time complexity as a criterion to decide who is going to lose the job. Instead, he's just going to use a stopwatch, okay, to see which algorithm finishes first, and then use that to determine which employee to keep. So what I'll do first is to use a spreadsheet to kind of make it visual, okay, so you can actually see the numbers. So we'll go use Office Calc or LibreOffice Calc and run some numbers. Okay. So what we'll do is we'll have a problem size. The problem size in this case is bar A bar, which is basically the number of elements in the array. Okay, that would define the size of the problem. In some cases, it's not bar A bar. In some cases, it can be some other things. But when we're dealing with a search algorithm with arrays, the size of the array is the size of the problem. Yep, go ahead.
Real quick, you said in C that it's bracket A bracket, not bar A bar. Bar A bar is only for this class.
There's no equivalence of bar A bar. The closest thing in C is called size of. There's an operator, quote unquote operator, called size of, and then open paren, close paren, and then you put something in it, it will tell you how many bytes it takes up in terms of memory. But it's not truly the same as bar A bar, because bar A bar tells you how many elements you have, not how many bytes it's taking. So in C, there's no true equivalence of bar A bar. Yep.
How about magnitude?
There's no magnitude in C and C++ as far as I know. There is a count function in some of the scripting languages. So that's basically what it is count or length of or count, All right, so this one is basically the problem size. And then here we have number of iterations or we'll just say number of iterations. And this is time. And then this is number of iterations again. And this is time again. And I need one more row because this one is mine. Oops. OEM. This is tax. And this is my colleagues. To stay gender, neutral, we'll say Pat. Nobody knows the reference to Pat. Some people do, but most don't.
Saturday Night Live.
Yep, Saturday Night Live, Pat. All right. So TAC is using binary search, okay? And Pat, on the other hand, is using linear search. Okay, so we chose different algorithms, but Pat's computer is considerably faster than mine. Okay, so let's say it's 1,000 times faster. Okay, so I'm at a very big disadvantage here. When the array only has one element, how many iterations do I need with a binary search to find out whether the only element is the one that I want or not. Takes one comparison. Does it make sense? Okay. And let's say because of my computer being extremely slow, this takes me, I'll just make up 1 unit of time. Okay. So whatever the unit is, it doesn't matter. Okay, because it's the ratio that matters. Okay. Now Pat's computer or Pat's algorithm is linear search. How many comparisons does that particular algorithm needs to confirm that the only element in an array is not the element that I want to look for? Also, only one iteration. All right. But because Pat is using a very fast computer, it's only using 0.001 of the time that I need to do one single iteration. Is that making any sense so far? Okay. So at this point, if my boss has a stopwatch, I'll be losing my job because my algorithm takes 1,000 times the amount of time compared to Pat's implementation. Okay. Now we are not talking about algorithm. We're talking about implementation. My implementation is far slower, but that's because you have to factor in that I have a much older computer and it runs a whole lot slower. Okay. So next we'll go to, well, most people would think, oh, the next number is going to be 2. No, not 2. Let's try 3. Okay. The reason why I say 3 is because 3 is a very magical number in binary search. Okay. The reason why it is so magical is because if you have 3 items in an array, okay, and you're doing binary search, what do we do in binary search? We compare to the first, the last, or the middle element. The middle one, right? So with binary search, we compare to this one here. Let's say this is not the one that we're looking for. What do we do next? We eliminate 1/2 of it, right? So we only have either this one left or this one left. Then my problem size becomes 1 again. Okay? So that's why 3 is special, because we can do this. I'm going to leave this picture up here because I will extend this picture as time goes. My algorithm will take 2 comparisons. In this case, worst case, right? The first comparison will check this one, then I will only have 1 left. Then the next comparison will confirm whether the remaining element is the one that I want or not. Okay? And time is really just linear to the number of iterations. So from now on, I would just say that in my case, it really is just multiplying the number of iterations by 1. Okay, so nothing really interesting going on here. How about Pat's algorithm using linear search? Remember what linear search is about? Start from the beginning, next one, the next one. Oh, okay, there's no more. Now I know it does not exist. So the worst case for linear search is how many iterations when we have 3 elements in the array. Worst case. It takes 3 iterations, right? The first iteration says, oh, the first element is not, does not have the value that I'm looking for. Second iteration looks at the second item, doesn't have the value that I'm looking for. The third iteration looks at the last one, and it says, well, it doesn't have the value that I'm looking for either, and then I can exit the loop. So that's why it takes up to 3 iterations in linear search. Is that making any sense? Okay. So basically with linear search, it's just, the worst case is the number of elements in the array. So in that case, I can just point it to the size of the array. And then the amount of time it takes is basically, this is the scale, and this is the number of iterations, and that will be the amount of time, the actual real time that it takes to execute that particular program. Are we still doing okay so far with these numbers, especially the meanings of these numbers? Still doing okay? All right. What do you think is the next number here to make it work out perfectly? Yep.
7.
Close. 7. Okay. The reason why it is 7 is because we want, after one comparison, that we end up with this, right? So that means the actual array would look like this, because we can go for the first half, we can go over the second half. But in the middle is the element that we're actually comparing to in the first iteration. So the first iteration will compare to the middle one, then it breaks it up into 2. Each one only has 3 elements. But we already know that with 3 elements, we only need 2 comparisons with binary search. So that's why the next one up is 7 elements. So we just 7 here. And the number of iterations in this case is 3, and the amount of time is just 2. Is just the same number here. I'm just using the equation. I'm saving myself all the typing here. On the other side, this is really just the number of elements in the array, and that's just proportional to that. So you can see that I'm getting very lazy because I'm using the formulas in the spreadsheet to help me do all the calculations. I'm not doing any calculations myself. Okay, what about the next one? Because at this point I'm not happy. My boss is still saying, "Tak, you're going to be fired." Okay, so I'm not going to quit until I win, or until my computer blows up. But you know what? If it doesn't blow up in the past 15 years, the chances of it blowing up today is pretty slim. That's how electronics works, right? Usually, there's a certain sensitive period where it can break down, but after that, it's stable. Yep, go ahead.
Why does on the time for Pat's on number 7, why isn't it .007?
You're right. You mean this one here?
Yes.
Oh, you mean here?
Yes. Is it because your formula is taking
The formula is
top cell
taking.
times the
Oh, you're
body
right.
cell?
Okay, I got it. Good observation here. There we go. Oh no. It has to be this one, which is 3. Okay, never mind. There we go. Thank you. Because it's pointing to the one on top of it when I use that extension feature, and the references, changes. It shifts as you make copies of a cell, unless you put a $, which means absolute. Then it doesn't change. Yep. Thank you. But Pat is still winning by a lot. In fact, if you look at the difference, okay, let's take a look at the difference. The difference is basically my amount of time minus the time that Pat's computer needs to finish the same job. Pat was pulling away, in fact. Because if you look at the difference in terms of number of seconds, Pat is pulling away. I mean, Pat is so happy and saying, there's no chance you can win because, my algorithm is so good, you can see the number. I'm actually pulling ahead. Okay, the lead of Pat's computer is actually increasing and not decreasing at this point. So, but I'm not giving up. I'll just say, what about the next one? What do you think the next number is going to be? It's the same approach here. We have 7, then we have 7, and then one more in the middle. So it's 7 times 2 plus 1, which is 15. All right, very good. So we have 15 here. And then the number of iterations is going to be just one more. Okay, so in this case it's 4, and then the rest I can just copy and paste. So, yep, this time it looks right. And you can see that Pat is still pulling away. I mean, that lead is increasing and not decreasing at all. So what do you think is going to happen here? What do I use to figure out the next number? I think most people can now see a pattern here.
Times 2 plus 1.
Yep, 2 times the previous one plus 1. Okay, so we can just use that equation. 2 times the previous one plus 1 is 31. And then the rest, what about this number here? This number seems to be just sequential, right? I mean, 1, 2, 3, 4, the next one is 5. Because with 31, after one comparison, I reduced the problem size back down to 15. So that's why that's really just increasing by 1. But if I have to come up with an equation to do it, what would be the equation to calculate that 5? Sorry? That's one way to do it. But what if I want to relate it to this number? And instead of relating to the 4 here, if I want to relate it to this number, what is the math equation to do that? How does 4 relate to 15, and 3 relate to 7, 2 relate to 3, and so on? Does anyone see a power function here? Like 15 is almost 2 times 7, and 7 is 2 times 3, and 3 is almost 2 times 1.
It's 2n plus 1.
What is the pattern here?
2n plus 1. 2n plus 1.
But how does this number relate to this number? What if you add 1 to 15?
It's the number squared minus 1.
What about 7 and 3? What if you add 1 to 7, you get 8? How does 8 relate to 3? power, think power. 2 to the power of 3 is 8. 8 minus 1 is 7. Okay, so now we're getting it, right? This number is basically the log of this number plus 1 divided by the log of 2. Okay, so now we can actually use the equation here. So I'll just use the natural log in this case. So I'll do the natural log of this number plus 1, and then divide it by the log of 2, and then we get the number that we want. This number is just linear to this number, so this number is really just whatever this number is, because that's how long it takes for one iteration. This number, we can keep it the same way, because this number is really just whatever the size is for the array. And then these we can just continue to use the way it is, because it's really just a ratio of this number using this as a scale. This is really just a difference between this number and this number. So I can now just select the entire row and easily calculate the next value. Okay. Is everybody seeing the flexibility of using a spreadsheet for this purpose? Because I don't have to do once I figure out the pattern and how to do the calculations, I can just leave it up to the spreadsheet to do the calculation. I just have to worry about the calculations. How does one row relate to the previous one? How does one cell of one row relate to another cell of the same row? Once I figure out the relationship and the calculations, the rest is really easy. So now I can actually say, oh, okay, I can definitely see there's a particular pattern here. What are you seeing other than the fact that this is linear? This does not seem to be linear, but who cares, because the difference is it seems to be linear too. But what are you seeing here? What do you observe with these numbers? They're increasing at a faster and faster rate. Are we okay with that concept? Okay. So these numbers are increasing at a really fast rate, as opposed to these numbers, which are increasing but not nearly as quickly. Okay. So that means if I make this a little bit longer, you can see that, hey, this is an interesting row. Why is this row particularly interesting in this case? If you look at the difference and compare this difference with the previous one, what are you observing? It's starting to go down just a tad, right? So that means Pat's lead over me is no longer increasing. The lead is now starting to shrink a little bit, okay? And this is a turnaround point, okay? It's basically a turnaround point. And if you look at this whole thing, if I continue to do this a few times, you can see the lead is now going down a little bit, more rapidly, even more rapidly, and I start to win. At this point, when the problem size is 16,383, which is 2 to the power 14 minus 1, okay? My algorithm is starting to be faster than Pat's. My implementation is starting to be faster than Pat's algorithm implementation. Okay. Can everybody see that? Using the table, the numbers. Okay. What if I extend this just like 2 or 3 more rows? Just to be sure. You can see my lead over Pat is increasing, and it's increasing at a exponential way, which is really kind of interesting. All right. So are there any questions about this picture? No questions? Okay. All right. So what makes a difference here? I mean, out of this entire discussion, what makes the difference? I mean, is it really how fast our computers are, or is it the shape of the curve? It's the shape of the curve that actually makes a difference. Because what if I say that, okay, I'm using a 20-year-old computers now, okay, and my base time is now 0.000001, okay? Pat is laughing his way or her way and say, hey, I'm still winning. Well, what will happen is, it just takes me a few more iterations to increase the problem size a little bit more to start to win. But winning is inevitable. Having the binary search implementation to be faster than the linear search algorithm is inevitable. The only difference is when does it take over. Okay? And that's the whole point of time complexity. Because what time complexity is to express this thing here. I'll try to write it out. And to use the right notation, I have to use Office. I have to use Writer. Okay. So let's say T and let's say N is the size of a problem, and T of N is the amount of time for an implementation to solve a problem of size N. Okay, so it's just a notation here. In our case, T. Okay, so I'll leave this one here for the time being. All right. So in linear search, okay, so this is for linear search. For linear search, T of N is what? Well, I should be more specific because it's not just linear search. It is linear search for Pat's linear search. Okay. So if I go back to the spreadsheet, and Pat's linear search algorithm is on this side. Okay. So when you look at these two columns, okay, excuse me, I take it back. When you look at these two columns, that's basically one column is T and the other one column is N. Okay. The first column is N, which is the size of the problem, and then the column E is T of N, which is the time it takes to solve a problem of size N. So how do I make that equation here? Let me make this a little bit smaller so we can see both at the same time. Okay, this one is not too difficult because it's really just 0.00001 times N, right? Because it's completely linear. What about my algorithm? Okay, what about tax? Binary search implementation. So these are all implementation specific because the speed of my computer makes a difference. Okay, so in that case, T of N is what? You have to focus on column A and column C in this case. But we already know that equation, right? It is basically the log of 2 applied to N. Well, okay, to be more exact, it is N plus 1. But N plus 1, whether you add that 1 or not, doesn't make that much of a difference when N is really big. Okay, it makes a huge difference when N is small, but when N is up in the hundreds of thousands, it doesn't make it that much of a difference. Okay. So, but this is not very useful because it is implementation specific. Okay. So now we want to look at the big O notation, which is the time complexity. Okay. So the big O, the time complexity of binary search. Okay, what exactly is the time complexity of binary search? In this case, it is called the big O notation of log N. So just log, any log, pick any log, and it's good. So what that really is saying is the time complexity this means that for any implementation of binary search, T of N is really just a constant K, pick K, pick some K, times the log of N. That's what time complexity is about. Well, in a nutshell, okay, if you go to the upper division class in a 4-year university, they will say, well, that's not exactly what the big O notation is about. But for this class, we'll just call it close enough. Okay. In other words, if I pick a faster computer or slower computer or do it by hand, all I'm doing is changing the k. Okay, k is a constant. Okay, if I'm doing everything by hand, I have a huge stack of cards and I'm doing everything by hand. K is a huge number in terms of microseconds, right? If I have a super duper fast computer, k is a fraction of a microsecond. But you know what? K is still a constant. It doesn't change. What does change is the other part. This is the part that is far more important because this part determines the shape of the curve. The other one only determines the scaling of the curve. But this part, the log of n part, determines the actual shape of the curve. And that's what time complexity is about. The big O notation that you see here simply means that the actual execution time of an algorithm, in this case, is proportional to the log of the size of the problem. Are we doing okay so far with just the concept? Okay. All right, so let's go ahead and take a look at the time complexity of some other algorithms, okay? Yep, go ahead.
Would it be log base 2 or log base 2?
It doesn't matter, because the base of the log is nothing more than a constant times whichever other base you choose. Okay, so to explain that, using math concept, okay, if you say, let's say you have a log based on k, okay, of a particular number x, okay, and you want to convert, the log to another log. Okay. So this is the log, the same as log of m, if you want to use that, times the log of, let's see, 1 divided by the log. Okay.
M with k. Log of m with k is the.
Oh, m divided by k?
Yeah, same base on the logs.
Okay. So is that m divided by k?
No, k is your variable. So it's log base m of k. That way the base of your logs are the same.
How about we just say there's a constant here you can multiply? We'll leave the calculation of the constant to the math people. But all I care is it's convertible by just multiplying the whole thing with the k. In other words, you're not changing the proportional part. Right. Is that making any sense?
I know what you're talking about.
Okay. That's all that we need to know, at this point. I mean, we can work out the math later on, Okay. So getting back to the time complexity thing, let's look at the time complexity of some of the usual or very common type of algorithms. Let's take sorting into consideration. Sorting algorithms, okay? We haven't really talked about any sorting algorithms, but is sorting important? Why do you think sorting is important in the world of computer science? Yep. Exactly. So if you think that you have an array and you'll be doing like thousands and thousands of search and the array is not changing, okay? Do you want to spend the time to do sorting once and then you can use binary search, or do you want to use linear search all the time? Okay, the trade-off is obvious, okay? You want to do the sorting first and then you can apply binary search for all the subsequent searches. So that's why sorting is a very useful algorithm. It is just one of the most important algorithms to talk about in lower division classes. But there are different sorting algorithms. So we'll just say that with bubble sort, which is a very simple algorithm and most people can understand it right away, it has a time complexity of big O of n squared. So this is a square. I know I can do the superscript here, but I can also do something even better. I can go to Inserts, Object, OLE Object, Formula. Now I can select, let's see, it is big O of n to the power of I think to the power is just that. There we go. How's that? Looks better? Okay, so bubble sort has this particular time complexity, which means what happens when you double the size of an array? What happens to the amount of time it takes to sort an array? Quadruples, exactly. If you triple the size of an array, it takes 9 times as long to sort an array. Okay, that doesn't seem too bad. Okay, if you think this is bad, we'll talk about something really, really bad later on. Okay, this is bubble sort, and then we have another search algorithm called merge sort, which is also it's more intuitive than most people think, but most people do not think of merge sort as an intuitive algorithm. But we'll just focus on the time complexity here. So I'll just go ahead and give you the time complexity, and you can decide on your own and say, oh, this is a lot better, this is just better, or this is worse than the other one. It is big O of n times the log of n. All right, so given that these are the facts that you know, which one is a better algorithm to use? Merge sort. Okay, merge sort is a far better sorting algorithm compared to bubble sort. Okay, it's because it's once again going back to n versus log n. Okay, because if you divide n from each one, this one becomes just n, this one becomes log of n. So if you look at the relative difference between these two sorting algorithms, you are going back to the difference between a linear search algorithm and binary search algorithm. Okay, and the difference is huge when n is a large number. Are we still doing okay so far? Okay. In this class, we don't care about how do we prove these are the time complexity for a particular algorithm. But there's one more thing that is really interesting about the time complexity of certain problems. So now we are not talking about algorithms, we are now talking about problems. In other words, we're talking about searching, we're talking about sorting. Okay? There's a lower bound of the time complexity of any algorithm for a particular problem. What that means is if the problem is to sort an array, there is a minimum. Okay? By the time you get to a certain time complexity, you can just say, okay, I know that there are no more efficient algorithm in existence. You can actually claim that. Then you can just say, okay, I got the fastest possible algorithm already in terms of time complexity. There's no need to look any further. Now, I think that is a really profound statement, that you can establish a lower bound for the time complexity based on the nature of the problem, not based on an algorithm to solve the problem, but only based on the nature of the problem itself. And as it turns out, for sorting, n log n is the lower bound. You cannot find a more efficient algorithm than merge sort. Now, merge sort is only one of the many algorithms with a time complexity of n log n, so they're all quote-unquote equivalent in terms of efficiency, even though the constant, the k, the coefficient, can be different. Are we still doing okay so far with all these concepts? Okay. Now, merge sort deserves a little bit of digression, because merge sort has a very special place in old mainframe computers. In old mainframe computers, they don't have a mass store, they don't have hard drives. What do they use to store information as their mass storage device? Tape, okay? Now, what is the big difference between tape versus hard drive, or anything that's disk-based? Yep.
Sequential.
It's completely sequential, right? You cannot say, oh, I want to change my track and then move on to another track. Nope, nope. To get to some other point, you have to roll the tape all the way over to the other one. As it turns out, merge sort is a very efficient algorithm, even on tape. Okay, you need 3 tape drives to implement merge sort on a mainframe computer, and that's all. So that makes it a very, very useful algorithm back in those days where mainframes are, the only thing that can do computation, because merge sort can deal with huge data sets, and it executes really fast using only tapes. Okay, so that's that's one more thing I want to mention about merge sort. Okay, so big O of n squared seems to be pretty bad. I mean, because every time you double the size of the problem, the amount of time is quadrupled. So that seems to be pretty bad. So the question now is, how bad can things get when it comes to the time complexity of algorithms? Now we can think of things like these, right? I mean, we can look at, let's look at this one here. And by the way, none of this time complexity discussion will be in the next exam, so you don't have to worry if you don't really get what it is. Just kind of absorb as much as you can, because I think these are all very important concepts down the line. But this is a good time to talk about it because we are going to talk about binary search. Okay, so you would think that big O of 2 to the power of n, that looks pretty nasty, right? Because every time the problem is increased by 1, the amount of time it takes doubles. That is really nasty because the amount of time to finish an algorithm is actually exponential to the size of the problem. Can anything get possibly worse than this? I'll give you this one, and then you can decide for yourself, why this is actually worse than it. Okay, so we'll go to big O of n exclamation point. Exclamation point? What is exclamation point doing here in the math equation? It's factorial, okay? So as it turns out, n factorial is worse than any 2 to the power of any base. Okay, because a base is still a constant. Okay, you can choose a really big base. Okay, 20,000. Okay, that's a pretty big base, but 20,000 to the power of n is still considered better than n factorial, and that's because n factorial grows really, really fast when n becomes relatively large. Okay, I used to have a Casio calculator. I'm trying to remember the number now. Okay, a Casio calculator, when it's using scientific notation, it represents a number as something point something 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 times 10 to the power of a particular exponent, right? That's the scientific notation. It can only represent numbers up to 10 to the power of 100. Okay, that's the maximum. It maxes out the internal representation of numbers. And if I remember correctly, the largest factorial it can deal with is in the teens. It's in the, I think it's 80s, I cannot remember, 61 or 69 factorial is going to max it out. 69 factorial is the last number that can be represented by old Casio calculators. And now I'm curious about what is 69 factorial. So let's pick it up. Let's see. So we do have factorial here. I think it is 69. So 69 factorial is, yep, that's it. That was the last factorial that can be represented by an older Casio calculator. But what kind of algorithm will involve factorial? What do you think? Well, first of all, are there any other applications of factorial in real life? Nobody can think of anything about factorial that can be useful? How about gambling? Has anyone bought lotto tickets even once? You can admit it. Okay, so why do you think factorial has anything to do with lotto tickets? Yep. Sorry?
Probabilities, permutation, and combination.
Exactly. Okay. So let's kind of go through that stuff because I know it's a digression from what we're actually talking about, but I think as a computer science person, or in engineering or sciences or math, it is kind of important to understand that sort of concept too. So this is an application of factorial. Okay. We'll start small and then we'll make the problem bigger and bigger. And what I'll do is I'm going to use trying to find the right tool to do it. Okay, we'll just use a text editor for now. Mousepad is good. Okay, so let's say we have 3 items, A, B, and C. Okay, so we have A, B, and C. How many different ways can I arrange A, B, and C? Okay, well, we can actually try this out, right? Without changing A, we can rearrange B and C. Okay, so A, C, B is another way to rearrange, the same 3 things. And then we can look at, okay, what if B goes first? Well, then we can have A and C, and then we can C and A. What if C goes first? Well, then we can have C, A, B, and then C, B, A. So there are 6 ways to arrange 3 different things. Okay? 6 ways to arrange 3 different things. What if I have 4 things? Well, now, one way to look at what happens when you have 4 things is to try to enumerate all 4, right? But the other way, the quickest way to do it is to say, when you have 4 things, what can you choose as the first thing? How many choices have you got? You got 4 choices, okay? But once you have fixed the first item, out of the remaining 3, how many can you choose for the second one? 3. How many can you choose for the second last one? 2. And then you only got 1 left. Okay, so the last item, you don't have a choice because there's only 1 thing left. And that's why factorial is closely related to, is this permutation or is it combination, where the order is important. It is permutation. Yep. The number of permutations is n factorial. If you have n distinct objects and you want to figure out how many permutations you have for those objects, it is n factorial. But Lotto is not like that. I mean, in Lotto, how many balls are there in total?
49 balls.
49 balls? Okay, so 49 balls. And then you pick how many out of those?
7.
Is it 8 or 7? Just pick one.
5 in a Powerball.
Huh? 6?
5 in a Powerball.
5 in Powerball? Okay, so we'll use Powerball, so we pick 5. Is there an extra number? Yeah?
The Powerball number, I think, is another set of balls altogether.
Sorry?
Powerball.
Yeah, the Powerball is separate from
another set of numbers.
Okay, so the Powerball from all 49, right?
Yeah.
So the 5 that you picked out will be put back into the basket before they pick the Powerball. Or they can
The
pick the
Powerball
Powerball
is a
first.
separate basket with numbers.
Is it 49?
I'm not sure. Well, let's assume. Let's say it is for the site, for the sake of that hypothetical.
Well, I want to do the actual number. Okay, so we'll look up Lotto Powerball. Okay. And they have to, I know by law they have to specify the rules. So let's see here, rules. Nope.
Probably under how to play.
How to play, okay. How to play. Great. I think if I'm addicted to Powerball, I don't have to worry about buying a house anymore. 35? That's fast. Okay.
5 white balls out of a 59 and 1.
Okay.
59 and 35.
59 and 35. Okay, got it. Okay, so 59 and 35, right?
Yes.
Okay, so let's try to calculate the odds. Is it 5? Picking 5 balls? Okay. All right. So the first thing is, how many different, in this case, combinations? Because when you're dealing with Lotto, picking, let's say the ball of 5 and 9, and versus picking the 9 first and then the 5, it doesn't make any difference, right? Okay. So how do we deal with that to begin with? Well, let's see here. First of all, we want to figure out how many permutations we have. Okay, so the permutations, the Powerball is easy. Okay, we'll multiply that at the very end. Okay, so the number of permutations is 59 times 58 times 57 times 56 times 55. Okay, because we are picking only 5 items out of 59, so we only have to multiply all the way down to 55, and then we got, right? But this is only the number of permutations. Within the permutations, there are many permutations that will be corresponding to the same combination. A combination is when ordering does not make any difference. Okay, so 1, 2, 3, 4 is the same as 4, 3, 2, 1. So the question now is how many permutations do we get out of a 5-ball excuse me, I take it the other way around. How many permutations do we have when we have a 5-ball combination? That's pretty easy to calculate, right? So the number of combinations is the same thing here. So I'm just going to copy and paste. Divided by 5 times 4, oops, 5 times 4 times 3 times 2 times 1, because for each combination, there are that many permutations. So after you divide the total number of permutations by the number of permutations for each combination, then you get a net number of the number of combinations.
5,000,006.
Okay? It's still a pretty big number, okay? So then you have the Powerball, okay? So factor in Powerball. Then the total number of possibilities will be this number times 35, because that one is completely independent to all the other ones. That's basically the number of combinations. And that's why permutations, combinations are important, but they're all related to factorial. And has anyone calculated this actual number?
I got the first one for the pick 5.
Well, I can do the calculation.
Right, it's 5,006,386.
Is it?
The second one is 143,039.6.
So as a total, we have this number. So we got 1,000 million, so 175 million something.
Yeah.
Okay. So when the payoff is exactly 175 million, is it worth it to play it? Let's say it's $1 per lotto ticket. It's not. Why is it not? Do they issue exactly this number of lotto tickets? Do they have duplicate tickets or tickets with duplicate combinations?
Yes.
Yep. And how many do they have that are duplicates? Who knows? Who knows, right? Hmm?
Whoever picks the number.
Sorry?
It's whoever picks the same number. So it could be any number.
Can be any number, right?
So you remember that last jackpot, 3 people in different states won the
And you've got lotto pools.
$360 million jackpot?
Yep.
It's 3 ways between the winners in different states. So
Mhm.
it's possible to get 3 the same number combination.
Okay. So let's say you multiply this number by 3, then is it worth it to play it? Then you have to ask Uncle Sam,
Yeah.
right? Okay? Because Uncle Sam wants a good chunk of that too. So at the end, I think you need the payoff to be a lot more than this number to even make it worthwhile. Okay. So that's kind of interesting because I personally have never gambled. I go into casinos for 2 things. One would be the food, and the second one would be the arcade. Okay, so I would play with those kids, where the parents, are saying, I'm too busy, go to the arcade. Okay, I'll fight you. Street Fighter, the original, the Street Fighter. So I'll beat up some kids in the arcade and eat some inexpensive food and call it a day. All right.
Sounds like a great way to spend a vacation.
It's air conditioned. Well, okay, let me tell you another story that is related to computer science and casinos at the same time. All right? And has nothing to do with cheating. Everything is, legit, okay? So there was this one time I was working for an embedded system company. Okay, they make, they basically make what we call SBCs or single board computers, about yay big, and you can put those, into other machines, such as slot machines and other machines that the casino may use. And this one is actually, I'm not sure whether I can name the casino, so let's not name it, but it's one of the big ones in Las Vegas, at least at the time. And they ran into one problem, which is kind of interesting. Okay, it's like they have an infection that is going on and spreading from one SBC to another SBC. Okay, one single board computer, and then the ones that are physically next to it will get infected, and then the ones next to the infected ones will get infected. would basically die. Okay, they basically stop functioning. And they were using these controllers to collect statistics. Okay, how often is the machine being played, the time intervals and payoffs and stuff like that. It wasn't used for control purposes, but it was used for monitoring purposes. And everything was hooked up by a wide network. So they couldn't figure out what is going on, and things seems to go wrong when they have a power fail simulation, because they have to simulate power fail once in a while just to make sure all the equipment is working, right? They couldn't figure out why, and then eventually the company, my employer, had to send a few engineers over to fix the problem and keep that account, because they were using a lot of our products. So we flew down to Las Vegas, and then we got to stay for free at a hotel, obviously. But that turned out to be not a point of any interest, because no one got any sleep anyway. We were just spending like 3 or 2 days, like 24 hours a day to try to solve the problem. So we were looking at different things. We brought along what we call a ESD tester, electrostatic discharge tester. It looks like a little zap gun, because that's what it is. So think of a well-calibrated, well-controlled taser for electronics, and that's basically what that thing is. Okay, so you dial in a number, a certain amount of energy and voltage, right? And then you just walk up to a single board computer and go like, zzz, and then you test it. Oh, it's still working. Zzz, again, it's still working. Okay, so that's how we tested those things, because we were suspecting that ESD was the source of the problem. And we got there, and then we got their board, and then we kept zapping all the boards, and nope, couldn't kill it. Okay, because they were designed to be resistant to ESDs to begin with. Okay, they got special components to deal with ESD. So obviously, zapping it, is not going to be a problem. Then what can possibly cause the problem, right? So we were spending a lot of time trying to figure out what can be causing the problem. And I still remember I was walking, on the carpet. It was a hot summer day outside. And I was just walking around, and then I was trying to see how much static I can build up, as a person. So I walk up to a slot machine, and then just very carefully, getting my finger closer and closer, and then the arc was 1/2 inch long. Now that's a good arc. 1/2 inch was a good arc. Okay, it's about this long of an arc.
Beat my record.
It probably had to do with the shoes that I was wearing at the time, and also it was dry outside. It was very dry and very hot outside, and it was carpeted area. All of those things combined to the really high charge.
Quick question
Yep.
before you continue. Did you shock any of your friends for laughs?
Well, these days I shock my cats all the time. For some reason, cat fur and me, we just build up a lot of static. We'll just put it that way. So anyway, and then one day we were observing how they fix their boards, fix their machines. So we saw the guy opening up the chassis, and then he just started to mess around with all the electronics with no discharge first. So then we just figured it out. It's like, oh, so that's how they kill their boards, because they were working on those things without ESD safety, and that's how they kill the board. But because the boards are all networked, the ESD to one board, the energy gets dispersed to the quote unquote neighboring boards by networking, by conductor, right? So that's how they were zapping their boards. And so we just said, oh, okay, now we know what the problem is. You have to wear these anti-static straps and whatnot when you're repairing the boards, and make sure that you touch the chassis first, because the chassis of these things are all grounded. So if you touch the chassis first, whatever buildup you have is going to be discharged, and then you will be safe to work on this stuff in the inside. So that was an interesting story where all the tests that we did, it was basically pointless until we observed how they did things. And it was all in the human, it was human error, not a design error in this case. All right. So interesting story about casinos and computer science, but has nothing to do with permutations, combinations, or factorial. Now let me switch gear now and talk about a problem that is related to computer science, algorithms, time complexity, and in this case, traveling salesman. Okay, traveling salesman. So let's say Tim is a traveling salesman who has to go between 4 cities. Okay, just 4. Okay, A, B, C, and D. And let's also say that we know all the details. Okay, how much it costs in terms of time and money to go from each point to another. Okay, so A to B, we know how much it will cost. A to C, A to D. So we have a complete matrix of how much time it will cost. Excuse me, how much money, because time is money, so we can end up with just using money as a measuring unit to go between all these different points. So the question is, if Tim has to go and visit all 4 cities, what is the best way to go, in this case? What is the best traversal order with these 4 cities?
ACBD.
Well, since I didn't tell you the actual cost, you cannot determine, right, in this case. But how would you determine that? Let's say these numbers, every single one is not obvious. It's not like, one is like 20 times of the other one, and then one is, 10 times the other one. Let's say these numbers are all kind of close, okay? What do you need to do to determine the actual optimal path in this case? Well, worst case scenario, you just list all of them, right? You come up with all the different permutations. You figure out, all the total time or the total expense, for each possible trip, and then you just pick the one with the minimum. How many permutations do we need? Do we have? 4 factorial. In other words, we have 4 times 3 times 2 times 1, which is 24? Yeah, 24. So we have 24 possible ways to traverse 4 different cities, and you just pick the one that is cheapest. Does this sound really hard to you? You're evaluating 24 possibilities and pick the one that is the least expensive. Doesn't sound too hard, right?
Probably make your spreadsheet do it.
You can probably make a spreadsheet do it. What if I have 5 cities? Instead of 24, I have now how many? 120. What if I make it 6 cities?
720.
720. You can see how that number increases kind of rapidly, right? And by the time we get to 69, then we'll have something times 10 to the power of 98 possibilities or things to evaluate. Okay, so that makes this kind of algorithm kind of interesting, right? There's a special name for this type of algorithm. They're called intractable, which means you can find a solution, but not in a timely fashion. Intractable algorithms. Intractable. So if you look at the word, let's see. Intractable. There we go. And that's a fairly common term to refer to problems that are exceedingly difficult to solve. Okay. And that has to do with computational complexity theory, some of you will take that class, and some of you may not need to take that class. Okay, so they talk about these problems, and it's called an NP problem. Okay, to solve this problem, it's called an NP problem. NP, it has a particular meaning to it. So I'll just kind of introduce the terms here, just so you know there are these concepts and ideas. NP. N means non-deterministic. And P is polynomial. There we go. Okay. What it means is it will take polynomial time for a non-deterministic machine to solve the problem. Polynomial, if you want to look at it in a general way, simply means the time complexity is big O of n, which is the size of the problem, in this case the number of cities, to the power, to some constant power k. Okay? That is polynomial time. Are we still doing okay so far? K is constant, it doesn't change. N is the one that changes because it is the size of the problem. Okay? But it will take a non-deterministic machine this much time to solve a problem. So the question now is, what do we mean by non-deterministic? It's not really what you think it is. If this is the first time you encounter this term, non-deterministic in this case is basically a machine that has an infinite number of cores. Think of it as a machine that has an infinite number of cores. Whenever you have something that can be done in parallel, you can just say, hey, just create a new core and I'll offload it to that new core. Okay? So this kind of problem will take a machine that has theoretically an infinite number of cores, polynomial time, to solve it. Now, why is that important? Well, computers are deterministic. In other words, we have a fixed number of cores with all the machines that we have these days, which basically makes algorithms that are NP intractable using conventional machines. They're extremely hard to solve. Okay, so the point about this whole thing is, let's say your boss gives you a new assignment. Okay, there's a problem you have to solve, and you are smart. You're not smart enough to solve it efficiently, but you're smart enough to say, you know what, I can convert my problem into the traveler's salesman problem using a simple conversion algorithm. Okay, in other words, I'm given my own problem, but I can cast the problem into the traveling salesman problem, and therefore, if I can solve this problem efficiently, I can solve my problem efficiently. Okay? If you can establish that relationship between your problem and the traveler's salesman problem, and your boss comes down to your cubicle and say, you're so dumb you cannot find an efficient solution to my problem, you can just say, well, maybe, but I'm almost certain that nobody can solve it efficiently either, because over the past 50, 60, 70 years of computer science, nobody can solve this problem efficiently. So you can keep your job. Does it make sense to you? Because you're basically saying, even though I cannot find an efficient solution to this problem, it is unlikely that anyone can. By establishing the equivalence of your problem with the traveling salesman problem. Okay, so some of you will have to take that class, which is called Computational Complexity Theory. If you're in computer science, if you're majoring in computer science and getting a bachelor's degree of science, you will probably have to take that class. Okay, so this is an early exposure to those particular concepts, since we are going to talk about binary search, where the time complexity is truly interesting.
Your class is a better introduction to computer science than the actual introduction to computer science.
Which I also teach.
Well, I don't know about with you, but I'm taking it with a different teacher, and it's like the first 8 or 9 chapters of the 12-chapter book are just how to use a computer.
Okay, I have to do something here before I talk. The cone of silence. When I teach that class, I don't use textbooks.
You tried once.
You
tried once.
Yeah, and kind of failed miserably.
And then you ended up 2 weeks into the semester going
Right. Well, you can actually watch my video, because I put the video online too, so you can see how I teach the other class, the truly introduction to computer science class. This one has more focus on algorithms. All right, so binary search. Okay, so how do we do binary search? Now that we kind of know all the interesting properties of binary search being an extremely efficient algorithm, and it's kind of simple too. I mean, if you think about it, all you're doing is you look through the entire array, or the portion of the array that may still have the item that you're looking for. You look at that portion and you go, okay, let me pick the middle one, do a comparison, and then based on the result of the comparison, you can now narrow it down to one of the halves that is remaining. And then you apply the same thing, it halves again, and you keep doing that until you have one item left. If you have one item left, you compare the key, what you want to find with that item. Well, it's either that or not, right? And that's basically how it works. So the first thing we want to do is to use a spreadsheet just to go through this algorithm once by hand.
But it needs to be sorted.
It has to be sorted, correct. Yeah, binary search cannot be applied if the array is not already sorted. So I'll give you a sorted array without the indexes. There's no need for, well, I can use the row number as an indicator, as an ID. Okay, so I'll just give you like 3, 3. Duplicate items are fine. Okay, binary search has no problem with duplicate items. 5, and then we have 7, 10, 11, and 16. Okay, 7 items. All right. So let's say, what do you guys want to find just to test the algorithm itself? Give me a number to find. 3. Okay, let's go find 3. Okay, so try to decide how to put that information here. Okay, I'll just right here log for 3. Okay. Which item should I compare 3 to first? The one on which row?
4.
Row 4. Okay. So on row 4, I will do this comparison. But instead of just saying that 7 is different from 3, I'm going to say 7 is greater than 3. In other words, whatever is already at this position is greater than the one that I'm looking for. And I have to be told ahead of time that the array is sorted in a non-decreasing way. In other words, all the following items have to be at least 7. So given that 7 is greater than 3, I also know that everything after that has to be greater than 3 and cannot possibly be 3. So that's why after one comparison, how many items can I eliminate? 4. Okay, it's not just these 3, but this item, the one item that I'm comparing to, can be ruled out right away as well. So by one single comparison, these 4 rows can be eliminated. So I'll just go ahead and use a background color to indicate it. Okay, so I'm just going to pick this color. Okay. So of the remaining 3, which row am I going to compare to? 2. Okay. So in this case, it's pretty easy because you know what? I just found it. I'm done. Okay. Well, let's try another scenario. Okay, because one scenario is usually not enough to really give you a good feel of how to write the algorithm. So let's go for another one. Look for something that is not there, and you think, that's a tricky place to look because because you think it's a tricky place. Looking for 4. Okay, let's try it. Okay, if we look for 4, it's the same thing. The first one we compare to is the 7, or the one on row 4, because that's right in the middle of the entire array. So we still say the same thing. 7 is greater than 4, and as a result, these are now eliminated. So we have, there's a way to do it. Yeah. There we go. Of the remaining 3, we will look at this one first, because that's the middle one of the remaining 3. So we'll say 3 is less than 4. If 3 is less than 4, then we can eliminate the 3 and also everything before that. All right. And then we only have one item left. With this item left, we can say 5 is greater than 4. And as a result, we can eliminate this item and everything after that. Do we have anything left that is not eliminated? Nope, every single one is now eliminated, which means we have no choices left and have to make the conclusion that 4 is not in the array. Yep.
What if you're searching for 35?
For what?
35?
35? Let's try that. Before we go any further, let me save the file first. So we have to create a folder first. So let's go ahead and use the same array. And this time we want to look for what value again?
35.
35? Okay, so let's look for 35. And it will work too. Okay, so in this case, we'll say 7 is less than 35. And as a result, these particular rows can be eliminated. Are we doing okay? Of the remaining 3, this one is the middle. And we'll do another comparison. This is 11. 11 is still less than the value that we are looking for, which means these can now be eliminated. There's only one left, which has a value of 16. So we can say 16 is also less than 35, which in this case is saying, oh, all of these can now be eliminated. Now that I have no candidates left, I have to make the conclusion that 35 is not in the array.
So whether it's out of bounds or not is irrelevant, just clarify.
Whether it's out of bound or not. Whether the number is greater than the greatest value in the array does not matter. Okay? Any other examples? Now, in this case, I'm tracking the rows that I have eliminated, right? So let's take a negative of this and then track the rows that can still have the value that we are looking for. Okay? Do you guys want to go back and just highlight the other ones differently, or do you want to try a new example? New example works better. Okay? So we'll go ahead and create a new example. But you guys can still tell me what to look for. Look for something that is not there, but somewhere in the middle. Okay, 8 is fine. Okay, so we'll look for 8. So what that means is, in the very first step, since I have not done a single comparison yet, every single one row is a possibility, because the 8, the value 8, can be anywhere within the entire array. Is that making any sense before the first comparison? So here I make the first comparison. The first comparison says we compare to the middle element. In this case, 7 is less than 8. Now because of that, which part of the array should I still continue to shade as kind of a pale yellow color? Which rows?
5 through 7.
It'll be these 3 rows, right? Because I'm looking for 8, this cell has a value of 7 already. That means everything before that cannot possibly be 8 either. So the only part left will be these 3. Okay, so I will shade these as yellow, or pale yellow. Of these 3, I will compare to this one. Okay, and that has a value of 11. So we have to say 11 is greater than 8. And which row or rows should I shade with this pale yellow color? There's one left. Row 5. Very good. Are we doing okay so far with tracking which row can still potentially have the value that we are looking for? And now we compare to row 5. And row 5 has a value of 10. 10 is also greater than 8. Now we have nothing left. Okay? Is that okay? Does everybody understand how I track the rows that can still potentially have the value that I'm looking for? Okay. Yep, go ahead.
How about all iterations of 3? Like if you want it to kick out everything that does have a 3, then you go through the same thing and then you still.
If you want to find out the number of items that has the value that you're looking for, in other words, you have duplicate items and you want to find out how many of these items have a value of 3, then my recommendation is still use binary search to find one of those occurrences. But because you know the array is sorted, you only have to go backward and forward to find all the adjacent items and see which one has the same value. Because you know that those ones with the same value, they have to be adjacent to the values that you just found, to the array element that you just found. Okay? All right. So I think we have enough, kind of clues, because we have done it by hand several times, to kind of come up with an algorithm. We may not have enough time to finish the entire algorithm today, but that's okay. We'll just go ahead and get started. Okay, revision 1 of binary search. Now the binary search algorithm is in the notes already. If you have read ahead of me, you probably know the entire algorithm already. But I don't want to just present the entire algorithm here. I want to kind of show you the process of how to create an algorithm, how to design an algorithm when you're starting with nothing. Okay? So in this case, do you think this process is repetitive? Seems like each column is representing a iteration, right? A particular pass of the same logic. So I would say this is a pretty good indication it is a loop of some kind. Okay, So we'll just say this is a loop of some kind. And do you think you want this loop to end at some point, or do you think this is by design, it is an infinite loop? We want to get out at some point, okay? Because we want to make a conclusion. We want to make a conclusion of yes, this value is in the array, or no, this array does not contain this value, which means we have to get out at some point to make that conclusion. So we have to end up, we have to get out at some point. How can I get out of this particular loop? What are the reasons that I want to get out? Okay, that I found a value, or that value does not exist. Okay, so we'll just write it down exactly the way you said it. Okay, so when the value is found, or now the other one I have to be careful because I cannot just say the value is not found, because just the fact that you cannot find the value up to this point doesn't mean that the value is not somewhere else in the array. So the second one has to be much more specific, and you can say basically you can say or confirm the array does not contain this value. Okay. Yep. Mm-hmm.
But you just said if it's sorted, the values would be right there. Well, just the question to find a duplicate, it would either be the one above or one below. So it wouldn't be anywhere else in the array if you can't find it.
Okay. If I just say the value is not found, it's ambiguous. Because, okay, let's say you're doing linear search, right? You have 10,000 items in the array. You performed one comparison. You can confirm that the first element in the array does not have the value that you're looking for. But then you can already say the value is not found.
Within the first iteration.
Because you're not clear about the value is not found with only the portion of the array you have explored, or with respect to the entire array. So that's why you have to be much more clear and say that you have to be able to confirm that the entire array cannot have that value before you can get out of the loop. And not just, oh, I've looked at a few items, they don't have the value that I'm looking for, and therefore it cannot be in the array. Okay, is that okay? Because it's a very important distinction. Whether we just say it is not found or it cannot be in the entire array. Okay, that's a little bit vague because we're using a lot of terms here that is not vague. So in the second revision, we just want to make things a little bit more clear by the use of variables. So we'll just say that k is the value that we are looking for. A is the array, the name of the array. And whenever you have an array and you want to say the value is found, well, we'll leave it to the next iteration. We'll just finish this one and then we'll come back next Tuesday to finish this up. Okay? So right now, is there a quick and easy way to say the value is found? Can I simplify this to a comparison of some kind? Okay, we got k on one side, we got a on one side, and we know that we want the equality. But this cannot happen because k is a single value and a is an entire array. I cannot compare a single value to an entire array. I have to say a particular item in the array has the value of k, okay? Which means I have to use the the square bracket notation here. But if I use a square bracket notation, I also need something to say, yeah, I know you're looking at one item within the entire box, but which one are you looking at? Well, since I really don't know how to calculate the index at this point, I'll just use a variable m here to indicate, oh, guess what? M is a regular variable. It stores an integer, which tells me which element in the array I should be examining for this iteration. Okay? So I'll just write that exactly here, and just say m is the index of the element that I am examining in an iteration. Okay, that's it. So I'm going to stop here because we are running out of time. We'll finish the algorithm step by step on next Tuesday. Okay? But this is the programming or the algorithm design aspect of this class. We're doing it step by step and try to reason out, how do we add more details to an algorithm.